So let us start the final lecture of Štefan in the frame of his excellent course. And this lecture will be about some very special graph on 26 vertices. And I wonder, are there any other graphs having triple names in the name? So I know that there are some having two names, but triple of names. So I have never seen like this one.
Okay, so Jelena, to answer your question, I know a few families of graphs which are carrying three names. For example, in degree diameter problem, there are known so-called Mackay-Miller-Shirani graphs, also Lazebnik-Ustimenko-Voldar graphs.
I see.
And probably there are more, or in the areas where I am working, they are appearing from time to time.
I see. So it is the first example of this series.
Yes.
Okay. Okay.
Okay. I will call this graph, which what I am going to talk about, the Paulus-Rozenfeld-Thompson graph, and I will later on explain why. But probably in the literature you will find it in under other names if it is assigned some name. Maybe it is just usually called that the most symmetric one from the strongly regular ones with specific parameters. I think most of you already heard this talk 2 or 3 times in some events, so I tried to modify it a little bit. So now I am choosing a little bit different approach to this graph. So first of all, I will define some well-known concepts in algebraic graph theory, but which were not mentioned earlier in this series of lectures. So first of all, I need to define the so-called switching of graphs with respect to some partition of the vertices into 2 cells or sets. And this switching is usually called the Seidel switching. So if you have some graph and you are selecting 2 cells, then the switching with respect to these cells is doing the following job. It leaves all the edges and non-edges inside each of 2 cells. So inside the cells, nothing is going to be changed, but between the cells, if you had an edge, then in the new graph, in the switched graph, it becomes a non-edge and vice versa. So what was non-edge is in the new graph an edge. So here I have an example. The dashed edges are edges of the original graph. So one of the 2 cells are vertices formed by the black vertices, and the second cell is formed by the 2 blue vertices. So edges inside the black cells are preserved. So this means that edges 1, 4, 3, 4, 4, 5 are preserved. Inside the blue cell, we have nothing, so nothing is going to be changed. And originally, we had this edge, and now it is missing. Also, we had originally an edge joining one cell with the other cell here, so this will be not an edge anymore. Between 1 and 2, also we deleted 2 and 3 and 2 and 5. These are the pairs which were joined originally by an edge, and now in the switched graph there are not joined. And new edges which were in original graph non-edges, and they were between two different cells, are, for example, the edge 2, 4, 6, 3, and 6, 4, and I think everything was considered. So the graph which is on the right side is the switched graph of the graph on the left side with respect to this partition into two cells. So clearly, if you choose different partitions, then you may obtain different graphs. So it is important to ask which are those graphs which can be obtained by via switching from a concrete one. And it is not hard to see that if we introduce a relation between on the set of finite graphs, and graph gamma 1 will be in the relation with gamma 2 if and only if gamma 2 can be obtained via switching from gamma 1, then this relation is a relation of equivalence on the set of graphs. It is reflexive because you can choose the two cells in such manner that one is empty and the second is the full graph. Of course, this changes nothing, so this relation is really reflexive. Also, it is symmetric because if you can obtain gamma 1 from gamma 2, then via the same partition you can obtain gamma 1 from gamma 2 because everything is preserved inside the cells, and if you change the edges to non-edges and back twice in a row, then you obtain back the original graph. So this relation, and also it is transitive. This is, I think, the hardest part of this proof, but still it is easy enough because it is you have just to think of vertices which are in both cases for if you go from gamma 1 to gamma 2 via cells C1, C2, and from gamma 2 to gamma 3 with cells or switching with respect to partition into C3, C4, then if two vertices appeared twice in the same cell in one switching and other switching, then of course the edge between or non-edge is between them preserved. And if they appeared once together and once in a different partition, then it was changed. So you can make a relation between the vertices in such manner that how many times they did meet inside the partition, and if it was an odd number of times, so precisely once, then they will be in the same cell, and if they were twice meeting in the same cell, and or in both cases they were in the other cell, then of course between them either 0 times or twice the edge was changing. So according to this we can separate the vertices, and with that partition we will easily see that with respect to this partition gamma 1 is switched to gamma 3. So this is really a relation which is an equivalence relation, and the classes of the equivalence classes of these relations are called switching classes of labeled graphs, because it is important that how the vertices are named, or here we do not consider isomorphism. We need really to work with the labeled graphs. So this will be one concept which we will need. Another concept also appearing in algebraic graph theory is called the two-graph. And the two-graph is not a graph, but an incidence structure. So we have a set of points V, which will be called also sometimes vertices, and a collection of three subsets of V, and these will be called triples. And with the property that each four subset of V contains as subset even number of triples from T. And two graphs can be obtained in quite easy way from simple graphs in such manner that we will take the two graph on the same vertex set as the simple graph has, and we will consider each three subsets of vertices, and if the induced graph on a selected triple of vertices contains an odd number of edges, then we are putting this triple into the two graph, otherwise we are not putting it there. So easy combinatorics shows that this really gives us a two graph. So for example, here we have a 5 cycle with an isolated point. So if we consider edge vertices 0, 1, 2, then we see that on the induced graph there are two edges. That means that we are not putting the triple 0, 1, 2 into the incidence structure. But if we take vertices 0, 1, and 3, then on the induced graph there will be precisely one edge, and this is an odd number. So the triple 0, 1, 3 will be a triple in the two graph, and so on. We will obtain all the triples which we need to put into the two graph. So I hope this is quite clear. We have to say that the same two graph can be obtained from different graphs. And what is nice that two graphs are in a nice relation with switching, because switching is preserving the two graph. So why is this working? If a triple which is appearing in the two graph T, if we are going to switch the graph with such cells that each three vertices are in the same cell, then of course to this triple nothing is going to happen. And there is just one more option. When one vertex is in one cell and two vertices in the other cells, then if there were two edges between these two cells among these vertices, then of course from 2 it became 0 in the switched graph. If there was one edge, then in the new graph will be also one edge. And if there were two non-edges, then we will obtain two edges between these three vertices. So the parity of the edges inside the triple stays invariant. So that's why two graphs are mentioned in the same page with the switching classes of graphs. So to each switching class naturally belongs a two graph. For example, if we take the empty graph on 4 vertices, then if you try all the pairs of cells which you can have on 4 vertices, then you will obtain these 8 graphs. So this is one two graph or one equivalence class or switching class on 4 vertices. And it is enough to check on one graph, for example, this one, how does the two graph look like? And it's easy to see that among any 3 vertices, the number of edges is 0, so the corresponding two graph is empty. I'm sorry. And we call a two graph regular if it forms a two design. That is, that each pair of vertices are appearing in the same number of blocks. And these how things are related to combinatorial design. So again, we find bridge joining graphs with combinatorial designs. And a nice property between two graphs and strongly regular graphs was found by Schultz. And we need a strongly regular graph which have relation between parameters. This one, that k is double of the parameter mu. So taking this graph and adding an isolated vertex, we can, of course, to this graph construct the corresponding two graph, and his theorem says that this two graph will be regular. For example, the pentagon satisfies this condition for between parameters, because really k is 2, mu is 1. So the corresponding two graph is a two design, and this we already seen in example 2, and we can check it, for example, on some pairs that, for example, the pair 0, 1 is appearing twice inside the blocks, the pair 4, 5 also twice, and if you will check all the 10 possible pairs, then you will obtain that the same number 2. So this is really a two design. Now, we need to introduce another concept which is probably for most of you well known, and these are the Paley graphs. Let us take a prime power or a finite field of order Q, where Q is congruent to 1 modulo 4. And we can construct a graph in such manner that the vertices will be the elements of the finite field, and two vertices will be joined by an edge precisely when their difference is a non-zero square in the finite field. So this graph is called the Paley graph of order Q. And an easy example is when Q is 5. In that case, the squares in the field Z5 are 0, 1, and 4, but we are excluding 0. So the Paley graph on 5 vertices is the same as the Cayley graph over Z5 with connection set 1, 4. A little bit more complicated example is obtained when we are considering the finite field of order 9. So let us consider the finite field of order 9 in which x squared plus x plus 2 is 0. So we can write down or physically construct the field, and after that, by taking all the second powers of all elements, we will obtain that the squares are the polynomials 1, 2, x plus 2, and 2x plus 1. And the obtained graph will be the Latin square graph, or sorry, lattice square graph, not the Latin square graph, L23. And in the corresponding labeling, it looks like this one. So it is a quite nice graph, and it is not hard to check that the Cayley graph of order Q is a strongly regular graph with parameters which are linear functions of Q. And an important property is that here the degree K is precisely double of the parameter mu. So that's why we are considering them on this place. So if we join together this property with the Schultz theorem, then this means that if we take the Cayley graph on 9 vertices and adding to it an isolated vertex, then we can obtain a regular 2 graph belonging to this graph. And inside this regular 2 graph, or inside the switching class of this graph, there are many other graphs on 10 vertices. And for example, if we are choosing a partition which contains 3 co-clique from the Cayley graph and the remaining 7 vertices on the other cell, then via Seidel switching, we are obtaining the Petersen graph, even though maybe on this picture it is not so visible that we really obtain the Petersen graph, but I am not cheating, so you can see that this is really the same graph, but with in other drawing.
Štefan, do you know by whom it was shown at the first time that we can take Petersen graph using this approach?
I think it was clear already to Ernie Schultz.
By him, okay. Mm-hmm.
Yeah, because this is one of the smallest non-trivial example of his theorem, so I'm sure that he was aware of this.
Right, yeah, I see. Okay, thank you.
It will be very surprising if this will be not the case, but I cannot tell it for 100%. So this is just my wild guess. Okay, so now in order to make further steps to our graphs, which we are considering, then a few words about the history why to study this graph or how it was obtained. At the beginning of the early 70s, already all the strongly regular graphs with the order less than 25 were known. And with all feasible parameter sets, there were known the exact numbers realizing these parameter sets. And usually these numbers were 1 or 2. And all the graphs were highly symmetric, meaning that quite rich group of automorphisms. And the first challenging problem at that time for mathematicians was to determine the precise numbers of graphs with parameters 25, 12, 5, 6 and 26, 10, 3, 4. Another challenge was given by Norman Biggs, who is one of the fathers of algebraic graph theory, and he was informally conjecturing that in all feasible parameter sets, when there is at least one graph, there will be at least one graph which is vertex transitive. So he formulated a problem. Okay, he was not believing in this, that this is really the case, so he formulated it in other manner, that find the smallest parameter set on which this is not the case. So all the realizing graphs are intransitive on the set of vertices. So just immediately, few years later, Paulus started a search for all strongly regular graphs with the mentioned parameters, and he found 15 such graphs with the parameter sets of order 25 and 10 on order 26, but he was not mentioning or not claiming that this list is complete. In the same year, in Russia, Rosenfeld approved this result, saying that the precise numbers of non-isomorphic graphs with these parameters are really 15 and 10 respectively. And the most symmetric of them on parameter sets 26, 10, 3, 4 was also obtained just a few years later on in the PhD thesis of Thomson. He was considering it in the terms of some combinatorial constructions and designs. And that's the reason why we now call this graph as a Paulus-Rozenfeld-Thompson graph, because each of these three people had some input to this graph. So that graph has 120 automorphisms, and the automorphism group is isomorphic to the alternating group of degree 5 Cartesian product with Z2. And what we know about their two graphs is that the 15 strongly regular graphs with the mentioned parameters determine only 4 non-isomorphic regular two graphs on 26 points. And the most symmetric two graph is obtained from the Paley graph, and in that switching class there is no more strongly regular graph with that parameters. And in that two graph, or from that two graph via switching, we can obtain the Paulus-Rozenfeld-Thompson graph. So this in fact says us that we can do the same job as with the Paley graph of order 9 in order to obtain the Petersen graph. And if we are doing the similar job with the Paley graph of order 25, that is, we add to it a new vertex, and now we have to select two 5 cliques which are disjoint, and after that, via switching, we are obtaining the Paulus-Rozenfeld-Thompson graph. So exactly how the Paley graph of order 9 is related to connected to Petersen graph. The Paley graph of order 25 is related to the Paulus-Rozenfeld-Thompson graph. So this we can regard as one of possible construction of this graph. Second construction can be given in the terms of coherent configurations or actions of group and similar stuff. So we already know that this graph is intransitive, so it is not surprising that we will need to consider two kinds of objects. So first of all, let us consider the alternating group A5 and its two actions which will be glued together. First, let us consider its action on the set of ordered pairs of different elements from the set on which the group is acting on. That means that we have 5 times 4 different ordered pairs. This set will be called omega 1, and the set omega 2 is formed by a pentagon and its images under the action of the group A5. So here we selected the, I will say, most natural pentagon, which can appear on 5 vertices, and its 5 images under the group A5. So altogether in that orbit there are 6 such pentagons. So by union of these 26 objects, we are obtaining the ground set on which the alternating group will be acting on. So we already know that if we are taking a permutation group, then we can obtain from it a Schurian coherent configuration. So exactly doing this, we are obtaining the Schurian coherent configuration W, which is corresponding to this action. And this coherent configuration is of rank 14. And of course, it will have 2 fibers corresponding to the orbits or to the sets omega 1 and omega 2. Maybe some less interesting fact that the restriction for the fiber omega 1 is giving a non-commutative association scheme of rank 8. And for us, more important thing is that by union of relations, we can obtain 2 disjoint copies of our graph. In fact, by merging, we are obtaining 2 strongly regular graphs with the requested parameters, but since the coherent configuration was obtained from the alternating group of degree 5, then it is clear that both of these strongly regular graphs have A5 as a group of automorphisms or subgroup of automorphisms. And from this, we know that necessarily these 2 are isomorphic and isomorphic to our graph, because the other 9 graphs with these parameters are having a much smaller group of automorphisms not containing A5. So now, using this coherent configuration and action, we can formulate precisely how to obtain the Paulus-Rozenfeld-Thompson graph. I think much nicer description is that to say that when 2 ordered pairs are adjacent in this graph, it will happen exactly when they are sharing precisely one coordinate, or if the pair is just, if the two pairs are just transposed to each other. So in the first case, when they are sharing precisely one coordinate, the corresponding edges on the picture are displayed by green edges. The pairs which are transposed to each other are joined by blue edges, and the incidence between an ordered pair AB with a pentagon from omega 2 will be precisely when the corresponding edge AB is contained in the selected pentagon. So this construction is maybe much more different than the previous one, but still it is, I think, nice enough to be presented. And we can consider the graph which is induced on the set omega 1. And I would like to tell that in Pilsen we had 2 or 3 years ago a conference which was devoted to regularity and symmetry, and this graph was selected as the logo of that event, and in the corresponding description the induced subgraph on omega 1 was displayed incorrectly, so there were some unnecessary edges in that paper, so this should be correct, and the correct picture is visible here. And also in our paper, I think the picture is wrong, so we are aware of that and we are trying to correct it.
Štefan, but what is wrong? I'm not quite understand.
In the original picture, there are such edges.
Oh, I see.
And they should be removed.
Oh, I see.
So yeah, to explain this picture, the red edges are just usual edges, and all the vertices which are in the same row or in the same column are joined each other. So black line means that all the vertices which are on that black line are joined. So for example, this one means that we have 6 edges between vertices which are having the second coordinate too. And
I see.
Now, and there are many more interesting objects living inside the same coherent configuration. One was visible already here. Oops, I'm sorry. Because here it is visible and it is displayed by dashed edges which are not belonging to our graph. It is just for showing that it was drawn on the canvas of the dodecahedral graph. So one remarkable thing is that we can obtain actually 2 different dodecahedrons as unions of 2 orbits, and also by suitable merging we can obtain directed strongly regular graphs with parameters which are shown on the slide. So, and moreover, the unique vertex transitive non-bipartite 0-2 graph of valency 6 and on 20 vertices, which is known under the name Brouwer's 0-2 graph, is also emerging in that coherent configuration. So there are many relations between these objects due to the fact that behind them somehow the same coherent configuration is appearing. So 0-2 graph just is a graph in which each two vertices are having either 0 or precisely two common neighbors. So in fact, it is a DESA graph, which I think is well studied in Novosibirsk. So,
and in Yekaterinburg, first of all.
Yeah. Yes, I'm sorry. I would like to apologize to Vladislav Kabanov and his group. Yes, I'm sorry. Okay, so here you can see dodecahedron, and with the aid of the dodecahedron, we can explain the adjacencies in our graph. So take I'm sorry. First of all, I will explain how the Brouwer's 0-2 graph looks like. Take the dodecahedron and select all the 4 tuples of vertices which are in mutual distance 3 or 5 in the dodecahedron, and put edges between them. So in this manner you can find 5 sets of 4 tuples of vertices, and among all these sets you are putting a clique of size 4, and these cliques together with the dodecahedron are giving the Brouwer's 0-2 graph. Now I am going to say how the construction of the Paulus-Rozenfeld-Thompson graphs work. So again, we need 26 objects. 20 objects are given by the vertices of the dodecahedron, and the remaining 6 are the so-called Petri polygons in the dodecahedron. You are obtaining Petri polygons in such manner that you are it is a term from combinatorial maps. So, okay, here you already see the decomposition into 6 polygons, but I think I will draw the same picture here where there is nothing written. So, for example, I'm choosing this edge, and I will write a walk and start in the middle of the edge and going from outside, going on the face. And when I am reaching the middle of the next edge, I'm switching the face and going further. So again, I'm reaching the middle of the new edge, and so on. I am going and doing this until the walk closes. And this is here. So this have to create a Petri polygon, and this means that the decomposition into Petri polygons are giving a 2 cover of the edge set of the graph. So here it is. And now we are obtaining our graph in such manner that vertices which are corresponding to the vertices of the dodecahedron are adjacent if and only if their distance is either 3 or 5 in the dodecahedron. Oh, I'm sorry, this explanation I was giving here was clearly not true because, oh, okay, I'm sorry. I was saying something wrong when explaining the Brouwer's 0-2 graph. Here the adjacency is related to distance 3 or 5. So take the vertices of the dodecahedrons and put edges between them when the distance is 3 or 5. And an edge is adjacent, or a vertex of the dodecahedron is adjacent to P3 polygon when in the dodecahedron it is containing it. And since these things are working in the dodecahedron, then after making the dual of the dodecahedron, you can repeat or translate the construction into the language of the icosahedron, which is the dual of the dodecahedron, and all terminology can be translated in the theory of dual maps. So this is all I think I intended to say about the Paulus-Rozenfeld-Thompson graph. And I would like to refer to my previous talk, which was recorded and put on, I think, YouTube. So you can find a slightly different, but maybe with other details on this page. Also, to my previous talk, it is related, the second reference, the full paper which we published together with Mishaklin and Matanziva can be found in a book related to a conference, and it has more than 80 pages. So here I was just saying a few words from it. And what I was mentioning, the conference in Pilsen and the description of this graph as the logo of that event can be found in that web page. And there are more items in which Mishaklin with some of co-authors are explaining a lot of connections between combinatorial objects and graphs and algebraic things. So if you would like to know more on quite educational level, then really you have to look at the papers Heinz Klein and Klein-Rücker and Tinhofer. So this is what I intended to tell during this course. So I would like to thank you all for your attention and that you were patient with me and you survived all these lectures. Thank you very much.
Thank you very much, Štefan, for this lecture and the course at all. And well, maybe there are some questions about this graph, or not only about construction. I'm just wondering which kind of open problems can be considered because of this graph? Because you gave us construction, but are there any open questions or problems on this graph?
Okay, maybe not on this graph, but I know that 26 is 2 times a prime and also a prime square plus 1. So from this reason, it has some unusual properties. And I know that at least some other elements in this sequence, Misha is considering a paper or doing research that what can be done in more general terms exactly from this.
Oh, I see. I see.
But exactly with this graph, actually I was speaking on Thursday and on Canadian Discrete Mathematics Conference, and somebody asked me that, okay, this graph is related to the dodecahedron and the icosahedron, and he is asking me whether it is related to a cube, because in cube you have 8 vertices, 12 edges, and 6 faces, and this is giving exactly 26. So maybe
you mean one more construction
in this direction.
I see. Okay. Any other questions to Štefan?
Can I ask a question?
Sure.
Yes.
You said that there are, I don't remember, not so many graphs with this same parameter as Paulus-Rozenfeld-Thompson. 10 or 15 or something.
Sorry, I can't hear you clearly.
Okay.
Yeah, me too.
Okay, now it sounded better.
So can you hear me?
Good,
Yes,
very
yes,
nice,
yes,
yeah.
Okay, good. So there are several strongly regular graphs with the same parameters.
Yes.
And also there are in total 4 regular two graphs.
Yes.
So does it mean this some strongly regular graphs are grouped into?
Yes, exactly.
And this particular one, Paulus-Rozenfeld-Thompson graph, this has several.
It's separated. No.
Several.
This one, which we were considering, is just a single one in that class.
Switching class.
In the other classes, there are more. For example, the graphs on 25 vertices are grouped in groups 8, 4, 2, and 1. So this is 15, and those which have 26, I think they are 4, 4, 1, or okay. I don't know now the precise numbers, but it is in this paper. Altogether with automorphism groups and such things. But yes, here are related to our graphs. They are just single objects, but in other places this is a number which is more than 1.
So there is one particular regular two graph that connects this Paley graph and Paulus-Rozenfeld-Thompson graph.
Yes.
I remember you mentioned that this classification of regular two graphs into exactly 4 up to isomorphism. it's purely computational, and I remember in the last conference you challenged the audience that someone would find a theoretical proof or some other better proof. Is that correct?
Yes, yes, yes.
So what is the computational proof?
I was not part of that thing, so I was not reading that result. This is I would say Misha's part of the work. So I was never meeting these
yes.
in fact.
Yeah.
I see.
Okay, thank you.
You're welcome.
Yeah. Any other questions to Štefan? Well, if not, then let us thank Štefan again, and for this lecture and for the course in general. And I have to say that since all lectures were recorded, then finally we will get the list of playlist of these lectures, and there will be announcement about the way how it is possible to watch these lectures. So it will be news, I hope. And Štefan, thank you very much. It was great to start this lecturium on algebraic graph theory, and I have to announce that next course will be soon, just in 2 weeks. Andrea Schwab, she is with us, and she will start to give a course on. Well, I have a poster of this course, so you can see what is the name of this mini course. So it will be mini course on construction of combinatorial structures from finite groups. Well, Andrea, if you would like to say something about your lectures, so that is a chance for you.
Yeah, well, I will actually use some theoretical things that Štefan has defined, and I will show you just one approach to construction of structures like combinatorial structure designs and graphs, especially strongly regular graphs arising from finite groups. So in first part, I will speak about transitive structures, and then I will speak about non-transitive action also. So I'll try to do my best.
Okay, so the course will contain 3 lectures, right? Yeah.
Yes.
Yeah, and we will start in 2 weeks, so on June 15, right? Yeah. So the first lecture will be in 2 weeks, exactly the same time. So the same link, and of course there will be announcement about this course. So please follow our announcement. And of course you can find all information on the same website where all information about the lecturium is available. So you are welcome to participate in the next course. Thank you very much for all audience, and I hope that in 2 weeks we will continue to get educational course on algebraic graph theory. Thank you very much for supporting of our lecturium. Thank you, and I hope that students maybe will come back. I mean, yeah, so the exams will finish and we will get a lot of students again. Okay, thank you very much.
Thank you.
If there are some
thank you very much.
information or some remarks. No,
Štefan, thank you very much for the nice course.
Thank you, Jelena, for organizing this.
well, actually, it is our pleasure to have your lectures. Thank you very much, for supporting. Yeah, it was very important. I'm sure that you do remember that at the beginning of this course, we had a lot of students because the first 3 or 4 lectures were very important for educational reasons of students in Russia, and not only in Russia. So thank you very much. Okay, so the course is finished, yeah, but the lecturum is still survive, and in 2 weeks you are welcome to join us again. Okay.
Yeah,
Thank you very much.
Bye bye.
See you in 2 weeks.
See you.
Yeah,
Thank you.
bye.
Bye bye.
Thank you.
Thank you.